Exactly. Well, it's warm day, sort of.
Okay, well, welcome to the first ever. We have feedback. I guess.
That's true.
Let's try again. Take that away. Okay, welcome to the first.
I don't have to join the Zoom anymore. You want me to turn it off?
As I said, this is the first hybrid colloquium. Okay, so I guess 3 years ago.
No, it's not me.
Are you in the Zoom?
Yes.
Okay, mute. That's why.
And Alyssa Goodman.
Hello, I can hear nothing.
Oh, I can also hear nothing.
Me too.
Yeah, me too. There doesn't seem to be any audio.
Mute and start the video. Roseanne, can you hear me?
Yes, thank you. I can hear you now.
Does anyone have any overhead transparency?
I think maybe we're going to get over here. This is the channel. No, there it is. Zoom audio device. Meeting owl here. Okay, input meeting owl. Roseanne, I heard you. Can you hear me?
Yes, I can hear you. You sound ready to give a great talk.
Al, wait. Hello, hello. No, I do not hear a ringtone. So is the sound by some chance off on the owl?
Unless
Roseanne, can you hear us now?
Yes, I can.
All right, you don't care what I say now, right? I fixed this. Okay.
Okay. We'll try again. So 2 years ago, on March 7th, Charles canceled all the CfA Colloquium, and I was very disappointed about that. And I emailed Charles and said, can't we just get less people in the room and get what everyone else can watch online? And what motivated that Hail Mary request is the fact that the person scheduled talk that Thursday was Alyssa Goodman. And I was one of the radio astronomers who, throughout my career, has always wished that my spectral line data cubes could be position, position, position instead of position, position, velocity. And Alyssa was going to talk about that on that Thursday, a new technique for making position, position, position data cubes using a combination of Gaia and dust extinction. So you can imagine how delighted I am to have Alyssa back here today for the first in-person colloquium since her own colloquium was canceled about 2 years ago. Now, how perfect is that? And now Alyssa has 2 more very productive years of research to present to us. So with that, I will turn it over to Alyssa to talk about the new Milky Way in 3D.
Thank you. So I'm going to take 2 hours because I have 2 extra. Actually, let me just see if I can hide this Zoom stuff on the screen here. Yeah, there we go. Unfortunately, I've had a lot of practice using Zoom. So first of all, I just have to say thank you. I mean, to see a room full of people is almost like the first day that I went back to teaching in person where I actually did silently cry. I'm not crying now, but I almost am. Okay, so thank you all so much for coming and being such great colleagues. And in addition to you, I have many colleagues all over the world, and some of you who are here have contributed tremendous things to this work, but aren't actually on any of the papers. And so I'm sorry if you're not on this list. This is a very long list of people because the work that I'm going to talk about is several years of work building to some of the results that you may have seen very recently. And so where's Doug? Doug here, there he is. Okay. So Doug Finkbeiner is the person who pioneered the 3D dust mapping techniques that you'll hear about locally, he and his group of students. And one of those students I was honored to share, Catherine Zucker, who is now a postdoc at Space Telescope, and she's listening to this talk. from there, and she was a postdoc with us until very recently. And a huge amount of this work has been done by Catherine and our collaborator, Joao Alves, who's listening from Vienna right now. And there are many, many other people, including a whole group of people here who I'd love to mention, but I think we're already behind schedule, so I better move along. And my computer is making a noise that says that the remote is not working. So I better go back here and find out why not. Okay, I think it'll work now. Yeah. All right. So what Tom was alluding to is what we would really like to know is the answer to this question. And many people in this room would like to know the answer to this question. What is the true spatial and kinematic distribution of dense gas in the Milky Way? And how does it relate to star formation galactic structure? That sounds like a pretty easy question, but those of us who work on it know that that is not an easy question. And I'm not going to answer that question today, but I'm going to give you a bunch of information that's relevant. And I have given you that information in a printed form because I have a friend named Edward Tuffy who had this phrase a long time ago where he said, view graphs leave no traces. So I'm going to show you all this great stuff, not on view graphs, and then you're going to forget. So you can take this with you and you can scan these QR codes and you can even try the augmented reality stuff that my cat here and I will demonstrate for you later. And Mike Foley, key collaborator right there, he has a merge cube with him and he's going to show you that too. Was there something wrong, Tom?
No.
Oh, okay. Thanks.
Just
Okay, so
violating
that's the
policy.
handout. So here's the talk. No, please, God, no, okay? I am not going to go through every single one of those papers. Instead, I'm going to explain what these little, what we'll call astroglyphs mean. And I'll point out, to go with what Tom was saying, this whole thing goes from like 2014 to 2020, sort of this way. And then that happened, right? But you see, all this fun stuff was since that happened. So I have to add that because that wouldn't have been there 2 years ago. So I'm going to tell you what all of these things mean. And by the end of the talk, there'll be a quiz as to what all those funny little symbols mean. And here's the guide. Okay, so Nessie is an infrared dark cloud in the plane of the Milky Way that we found out some interesting properties of several years ago now, but that arguably started this whole story. So I'll tell you why that is a bone of the Milky Way and what the skeleton of the Milky Way might be. But then I'll get as fast as I can to what Tom was asking about, which is how you connect what he and I and many other people here are used to, which is position, velocity data cubes that you get from radio astronomy spectral line observations with this magical 3D dust mapping technique that Doug and his group have pioneered. And then you get to discover a gigantic undulating wave that is the local arm of the Milky Way. So this thing with like millions of solar masses of gas that we didn't know was there, but that hosts many important star forming regions, including Orion. And then we're going to go, but wait, there's more, okay? Because we're going to improve the spatial resolution of the dust observations from several parsecs, which is already amazing, to 1 parsec. And then you're going to be able to discover all kinds of interesting things about supernova feedback. And then I don't know how many of you saw this in the press, but you're going to find out that all star formation near the sun lies on the surface of the local bubble. So that's what we're waiting for at the end. And then I'm going to give you a little taste of what Mike Foley and friends are doing that has to do with applying these techniques in even more detail. So to just give you a sense of the size of the things that I'm talking about, so here's a kiloparsec down at the bottom of the screen, okay? So Radcliffe Wave that we're gonna hear about is 2.7 kiloparsecs long, big long section of the local arm of the galaxy. And then we're gonna talk a little bit about the Perseus molecular cloud as an example. That's the smallest thing I'll talk about. These bones we used to think were big, assemblies of them would be bigger. Orion's pretty big. We thought this per tau shell was pretty big, but the local bubble is pretty huge. But again, importantly, nowhere near as big as the Radcliffe Wave. And in the background there, you can just barely see a Milky Way. That is not an actual map, okay, to scale. And that is, of course, much, much bigger than any of these things. So here's what Tom was talking about, okay? We would like to see the Milky Way in 6 dimensions, okay? Those would be X, Y, Z, the velocity in X, the velocity in Y, and the velocity in Z. And we'd like to measure a lot of properties in all of those dimensions. So until very recently, that was just patently impossible. Okay, and it's still impossible for gas, but it's sort of possible if you combine gas, dust, and stars. And so that's what I'll explain by the end. But let me start off with the bad old days, okay? Sorry, Tom, Phil, other people here, where you can only have position, velocity data and show you how you get that and what it's useful for. And then there was this kind of watershed moment in 2018 because I went on sabbatical and Catherine worked with Doug, thank you, Doug, to look at Perseus and to try to connect the velocity observations and velocity observations. And that worked out. And that emboldened us to do all this other stuff that I will talk about later, where you get to 4 dimensions, adding 1 dimension of velocity, and then 6 dimensions, recently adding 3 dimensions of velocity. So I have a few places in the talk where I have these little banners that are just kind of mini tutorials for people who don't do this kind of work. So I apologize for those of you who do. But just as I said a moment ago, what you really want is all of these things, X, Y, Z, and velocities in all of those dimensions. But what you get when you take a grid of spectra, whether you use an array or an interferometer or any kind of instrument, when you get a grid of spectra, you essentially use a Doppler effect and assume that the velocity distribution is shown by the spectral line shape, and there's a lot of opacity effects I'm not talking about, just pretend, okay? And then what you're getting at each position is a measure of intensity as a function of velocity. So the 3rd dimension is velocity, not actual spatial dimension, okay? So we only get this VZ, which is the line of sight velocity, and that's what gives you the so-called PPV, or position velocity space. Now I have this beautiful history of the Milky Way that I removed and put in this one slide. This is why I apologize to Tom Dame, who, by the way, is the first person I ever met in my research astronomy career when we were both in New York. So thank you, Tom. And what Tom was working on at the time was imaging the whole Milky Way, or the plane of the Milky Way, in CO with lots of other people who were working in Pat Thaddeus's group in New York. And so you've all seen this poster. Okay, but today, what I want to point out is that here's that, by the way, that was William Herschel's music. Charlie is upstairs watching. I'm sure he knew that that was William Herschel, the astronomer and composer's music at the beginning. Here's William Herschel's. If Charlie was here, I'd ask him if this is supposed to be from the side, from the top. I'm not really sure, but this was supposed to be the shape of the Milky Way, according to William Herschel, who was estimating this as the stars in 1781. It's not terrible. Okay. This is Mark Reed's version of a top-down view today from maser parallaxes. And so over here on this side, you have things where you're talking about actual distance, true 3D space, true distance. Okay, even though this is estimates of distances of stars, at least it's actually 3D. And then hopefully most of you know that maser parallax observations, where you have tiny, very bright sources that you can measure distance to using parallax techniques, which I'm going to assume that this audience is completely familiar with, is really the gold standard for measuring distances in the Milky Way today. The problem is not every region has a maser, and the VLBA is kind of expensive. And so you can use this in special places, but you can't use it to measure the distance to random things. Okay, so what people do instead is the kind of thing, oops, that you see over here, that was first done by Jan Oort and collaborators looking at atomic hydrogen, where they used the so-called rotation curve of the galaxy, and I'll explain what that means in a second, to translate observed velocity of the hydrogen in the spectra to distance, and they came up with that map, and the sun is up there in the middle somewhere. I'll make this glow if I can hold my hand still. See, that's the sun, okay? And so those are vaguely spiral arms of the galaxy as seen in H1. And then Tom's famous map has 2 views here. One is this is an unwrapped view of the plane of the Milky Way so that the left side connects to the right side. And then this x-axis is shared, but the y-axis here is velocity. And so you can see these funky features are things like spiral arms, okay? And if you can disentangle what you think the velocity profile of the galaxy should be, you can assign certain velocities to certain distances. And so here's just a really quick summary of how that works. Pretend that that gray thing is the galaxy and that it's rotated according to some rotation curve where it has, say, a constant velocity in the outer parts, okay? So then those blue arrows, I know it's an optical illusion. It doesn't look like those blue arrows are the normal to each circle, but I promise you they are if you look very carefully, okay? So if you look at the component perpendicular to the line of sight from the sun, And then you look at the velocity component along the line of sight, which is this VZ that we're talking about, right? The issue is that, yeah, you can kind of do this where you say, okay, those different distances have different velocities they can predict from this rotation pattern, but you'll notice right away that there are some problems when you look at the inner galaxy, for example. There are two places with the same velocities. This is called the distance ambiguity. So there's a lot of problems with this method, like that you have to know the rotation curve of the galaxy is the biggest one, and then these distance ambiguities. And the biggest problem for the kind of stuff that we want to do is that this doesn't work for individual clouds, for small scale things. So for the cosmologists here, it's like how the Hubble flow doesn't work for mapping, individual galaxies. So, right, so I'm going to give you this little preview before we throw in the 3D dust. Then I'm going to tell you what I started to explain before about Perseus. And then we're going to get to the really fun stuff, starting with what I would have talked about 2 years ago, and then the bonus stuff that's happened in the last couple of years. So let's start with Nessie. Okay, now I've given entire colloquium, possibly even here, I can't remember, but about Nessie, okay, which is this really amazing infrared dark cloud. And what I mean by that is if you look at a Spitzer image here, you see this shadow, which actually continues even off this picture of a long continuous structure that turns out to have an aspect ratio of about 300:1. Okay, and this was also not expected. It does show up in some recent simulations. I'll show you something in a second. Okay, something like it, not quite 300:1, and yeah, anyway. But the other thing that's really interesting about it is if you look at this picture here at the bottom, which I understand that the non-experts are not going to go, oh, I get it, but just trust me for the moment, okay? These colored dots here are measurements of dense gas velocity at the positions along this infrared dark cloud that's very dusty. And the color that you see in these lines, okay, is the predicted velocity for that kind of galactic rotation curve at the distance to the Supernova-Centaurus arm, which is where this is, okay? And so if the velocity of the dense gas matches the predicted velocity, then there's a white circle around the point, and if not, there isn't, and it's some other color. So you'll notice that all the ones in Nessie match perfectly with being in the Supernova-Centaurus arm. And then the other thing that's really interesting is that these lines here at the distance of 3.2 kiloparsecs to that arm are plus and minus 20 parsecs from the exact midplane of the galaxy. And by the way, that midplane also relies on knowing the height of the sun off of the plane locally, which we take to be about 25 parsecs. So that's what I mean when I say in the plane. Okay, so this dashed line with the exact midplane. And so what we think is that clouds like Nessie, these so-called bones of the galaxy, mark where the gravitational midplane of the galaxy is, at least toward the inner galaxy. So if we could find a whole bunch of them, they might be the spines of arms, and they maybe mark the sort of zero in the z direction perpendicular to the planet galaxy. So that'd be really interesting. So that's what we started off doing when Catherine was first a student, and we worked with Ron Smith, who has these repo simulations of a small section of galaxy. And you can see that these things that are highlighted in red and blue were measured carefully in 3D. This is a 3D simulated image. And you can measure the properties of these things and say how similar are they to Nessie and to a survey of other long skinny filaments that we and lots of other people made other surveys of. And what you see here on the left is a cartoon summary of, this is the height off the plane of these filaments. And then the shape is roughly just shown by the aspect ratio of this rectangle. And you'll notice that there are different kinds of things here. Okay, what's important is that the bones are these really super skinny ones that are super parallel to the plane. And then there are these so-called giant molecular filaments that are really molecular clouds that are kind of long and not as skinny. And then there's other things that are found by other techniques. And you notice if you just kind of look at the statistical distribution of these by eye, and you look at what's found in the simulations, it's like, yeah, almost, but not quite. Okay, so the simulations can't produce yet the variety of these long skinny filaments in the disk that are seen, at least as of, that was 2014. Although the simulations were analyzed in 2018, 2019. Okay, so now let's get to Perseus. So this is a complicated plot, okay, that again, for the experts, if you took this and folded it into a box, that's what this means, okay? You'll see how that works in a second, all right? But what you really just need to know for now is if you look at some old data that looked so 3D, right, Tom, that you so wanted that to be actual 3D, okay? That's the complete data from now a long time ago, showing you carbon monoxide emission, which is a proxy for dense hydrogen gas in the Perseus molecular cloud. And it shows you that, let me just go back and spin that again. So if you the dimension you're not seeing into the screen is velocity, okay? And I'm just showing you the 3D so you can get a sense of what this looks like in 3D. And then what you see here is projections, okay? So the top left panel is position, space. So that's what the CO emission looks like on the sky. The next one down is the so-called position velocity diagram, which most people who don't use them hate. So I apologize, but imagine you have like a cube and you folded it. And then if you look from the end of the cube, you would see this. So that's position velocity from the other direction, okay? But what's important is Doug and friends were looking at Perseus in 3D dust, and Doug, I could do a terrible job, but Doug will do a much better job. Give you incredibly detailed history of the statistical improvements of all of the 3D dust mapping techniques. I'll show you how it works basically in just a couple of minutes. But for the moment, just believe that we had individual measurements, which are these colored points, to kind of where were these whole regions. Does that mean anything? The host has spotlighted your vision, and we're good, okay. So in other words, you could measure you could average together a big region and say like, what's the distance to B5? What's the distance to IC48? Not what's the distance to every pixel. You have to wait about 20 minutes till we get to that, okay. We thought this was pretty miraculous. So anyway, if you do that, then you notice in Perseus, lucky us, there was this gradient in the velocity that corresponded to a gradient in distance. So this gives you the idea that someday it might be possible to connect velocity to distance, not in a kind of perfect Hubble flow, this is kind of an accident, right, that it's a straight line, but that there could be patterns in velocity that correspond to patterns of distance that are interesting. So it's not quite that we wanted to use velocity as a proxy for distance, but it was giving us a hint that the 3D dust mapping might be really helpful. Now, the part that I didn't tell you at all is how do you do 3D dust mapping? And I have to tell you that before I can explain why Gaia is so incredibly helpful. So this is an extremely detailed cartoon that Doug may not like. I'm kidding. Hopefully not. I'm also kidding about the part he doesn't like it. But anyway, so basically this parallelogram here is meant to be your imaging plane, and this giant box is meant to be 3D space, okay? And so somewhere out there in space, there's a star. By the way, I wore this shirt on purpose. The shirt is a more accurate rendition of what's going on with it. We'll see why in a second. So anyway, so I'm going to make all the stars the same color, but in fact, the stars will look like this. Okay. But so let's say all the stars that I'm going to put here are this weird greenish color, and I'm going to put some distribution of dust in 3D space. Okay. As the starlight travels through the dust, we all know in this crowd, I hope, that the starlight is reddened. Okay, so you get a different color of the star observed in the imaging plane, the same way that you would from sunset. So now imagine that you had a whole bunch of stars that were all the same color, just to make this easier, and then they go through different amounts of dust, right? Then you would see some distribution of those stars on your imaging plane with some distribution of colors. And then if you have genius graduate students and Doug, okay, and a lot of computing time and a lot of data, just imagine that you can infer a self-consistent 3D distribution of stars and gas that give you that distribution in 2D. But now imagine that I told you, right, that I remove, well, first I have to tell you that the stars aren't all the same color. Thank you, Josh Spiegel, Charlie Conroy, all these people who have worked on all these models for the actual color distributions of stars and how that get folded into statistics. I'm not talking about that today, okay? So don't worry, we don't actually assume that the stars are all the same color, okay? But anyway, so let's say you know all this, and let's say you have this technique, which is what was being used with the pan-stars data that did the Perseus stuff that you saw. Now, I tell you, you can cheat. And Gaia gives you not just a good prior, but like a really strong prior on the distances to the stars. So now you know the 3D positions of the stars, you know a lot about the colors of the stars. It's a lot easier to figure out the 3D dust distribution. And so this is the map that Greg Green put together in 2019. And Doug had this great idea to pretend that you were looking at it and then bob it up and down so you couldn't see just how bad the distance resolution was. It was pretty good, actually. It was really quite good. Anyway, so that's looking out from the sun, and you can actually already see that there's this big, long, interesting feature. Okay, so we're going to come back to that later. So before I continue, is Mark here? Maybe he's on Zoom. So I don't want to. I want to praise, not insult, maser distance measurements. All I want to complain about is that there aren't more masers. No. Okay. So if you had masers everywhere, you could keep using maser parallax for distances. But when we first showed all of the stuff about the Radcliffe Wave that I'm going to show you shortly to Mark and to Tom, who were our, for those of you who know in journalism what a red team means, that's the people who are going to tear apart what you did because it must be wrong, right? So remember this, Tom? So Tom and Mark come to a little meeting and we're like, okay, this is crazy. I haven't shown you the crazy thing yet, but this is crazy. What did we do wrong? And at one point, Mark says, well, can you show me that your distances match my distances? And so this was the very simple XY plot that we made on the spot, showing that if you have masers at particular positions, what does the 3D dust distance give you? And I don't know about you, but in astronomy, I call that a pretty good thing. Okay? So I'm good with this, okay? I believe the 3D dust distances. So, all right, so if you have these good distances where you fold it in Gaia, what can you learn? So now, for the Radcliffe Wave and for the local bubble, I'm going to talk to you later, we gave press conferences at the AAS, and so we have these kind of fancy slides, and so I've dressed them up with a little extra astrophysics for you, but some of them are from the press conference, so apologize if they're too fancy. But anyway, so here is a view of the Milky Way where we've now superimposed distances to individual clouds that were targeted for higher distance resolution measurements to try to figure out where a bunch of famous star forming regions are. And when you do that, first of all, you see that this thing is extremely long and straight from the top. And then when you turn it around to the side, you see this bizarre damped sine wave. And by the way, in the actual paper, there are fits of the damped sine wave. I can show that to you in a moment, okay? And for anybody who doesn't know, the thing in the background is a cartoon, right? Data-driven cartoon, but a cartoon. Okay, so the Radcliffe Wave, as I said before, is 2.7 kiloparsecs long, only 130 parsecs wide, and has an amplitude of 160 parsecs, and at least 3 million solar masses. Okay, so the two important developments that we highlighted when we talked about this in January of 2020 were that we can measure these distances to 5% now, okay, and that nobody expected there to be a giant sine wave in the arm of the galaxy. So if you look at before Gaia was folded in, and you look at kind of a cartoon view of if you looked out at those clouds, the clouds are just the little red dots, and then the lines are meant to be error bars showing you how uncertain the distances were. You know, you might see that there's some sort of pattern. But remember, I said also that what Catherine did, and this is Catherine with João Alves when João was visiting here as Radcliffe Fellow, hence the name Radcliffe Wave. There's more to it than that, but that's part of it. From 2018 to 2019, they decided, and you can basically make trade-offs in spatial resolution versus distance resolution. And so if you want to go beyond what Greg did, you can get higher distance resolutions for specific targets. And so that's what was done. And the Gaia data was also used. And so you go from, and by the way, of course, the distances are only measured along the line of sight, which is why you have this funny pattern, right? You go to that. Okay, so if you shrink the distances by that much, the distance uncertainties, you can start to see structures that you didn't know were there before. I think if I click on this, hang on one second, let me try this. Yeah. So I think I click on this. Oh, there's a CfA Colloquium. I should go. This is the interactive figure. And so a lot of what I'm showing you was made in this software called Glue that I love very much, and that I actually will show you a live demo of later, and then export it to Plotly. So this is Plotly. This is an interactive JavaScript plot, which is in the journal article in Nature. And so let me just turn on a couple things so I can show you some more. So here, when I said that a damp sine wave was fit, okay, that's the fit. Let me turn off the clouds that we're going to talk about later. So those are the ones that we're saying are in this wave structure. Here's this fitting was done by Josh Spiegel. So of course we have lots of other alternative fits, but the black one is the best one. If I turn the other clouds back on, you can see that there are a lot of other clouds that seem to be associated with other structures, and they are. There's another structure here called the split that we'll talk about later, and then some things that are farther away. But one thing I want to show you before someone asks is, what about the infamous Gould's belt? So Gould's belt turns out to be a projection effect. So if you look at this section of the wave and you, oh, don't do that. If you look at the clouds here that are in the wave, that side of Gould's belt's pretty good. This side's not so good. Okay, there's a few clouds here, but there's nothing here and there's nothing here. And so it was kind of a fit to what was known at the time, but really, I'm sorry, but Gould's belt, no. Okay, so and just for fun, this thing here where it says tenuous connections, what happened was first we targeted the clouds that everybody knew about. Let me turn off the fit. Okay, and we started to see a hint of what was going on, but then what happened here is we had to add a bunch of connecting features to see if this was really connected. And so we connected them on the planet sky, and then yes, they were connected in 3D. Okay, so that's pretty crazy in a kind of good way. And so this is just a screenshot showing the glue software that we use to do all this. And there's a fun story I can tell you if you ask me later about Joao saying that he thought he found something interesting and then coming to my office to have Indian food one night. And we invited Catherine over and we nearly spit our Indian food out all over my office when we just dragged the data in real time and went, oh, wow, it's this wave going in and out of galaxies. So it was a huge amount of fun. Just to show you why the Radcliffe Wave wasn't found sooner, if you just look at the positions on the sky of the components of it, it doesn't look like anything special. And so you actually need the 3D to do that. Okay, and so to remind you of the kind of recent history of the technology that makes all this possible, the maser observations really came into their own 20-something years ago. And then this software that makes it easy to spit Indian food while looking at your data, Worldwide Telescope and GLUE are more like a decade ago. And then the ability to do 3D dust mapping, not as well as this little icon, I'll explain the icon later. I don't know, Doug, you want to give it a date, but something between 2010 and 2015 is fair. Sure. Yeah, okay. And then Gaia just a couple of years ago. Okay. So you can see why we didn't know about this before. This is my extremely accurate picture of the Milky Way. Just want to give some terminology, some exposure here. Okay, so for those of you who use these kind of terms all the time, let me just put in context what I've said. Okay, so here toward the inner galaxy, so the sun is here somewhere in this picture. Okay, and so looking through the inner galaxy, you see this Nessie cloud. Okay, and you see a few other of these domes, these very, very dark, long features in the plane, exactly in the plane of galaxy. So then we said, wait a minute, we just said we found this thing with an amplitude of 160 parsecs out of the plane of the galaxy. Meanwhile, I said Nessie was within a few parsecs of the plane. What's the problem? Oh, well, the sun is there, like I said, and it's a bunch more Nessies, but if you look the other way, then that's okay. If in fact the thickness of the galaxy is really that big outside the solar circle. And it turns out it is. And I have to thank Bruce Elmergreen and Charlie Latta because Charlie had a great meeting for his birthday where Bruce said, have you looked at Mark Heyer and Tom Dame's annual reviews article? And you can clearly see that if you look at the solar circle, the thickness of the disk starts to get really big. And that our 160 parsecs shown by this red line in the top panel is not at all inconsistent with the thickness, which had to be true because those are the clouds that are in the Radcliffe Wave, but still it's nice to see it that way. Okay, so there's not a problem, except of course nobody predicted that there would be exactly that kind of wave. Gus Beam, who I'll mention in a second, has done some nice work, as have some other people looking at collisions with dwarf galaxies and things like that, but the wavelength and amplitude of what's predicted as ripples isn't exactly what you see in the Radcliffe Wave. So, maybe it's some collision with something, maybe it's some really dramatic feedback, maybe it's something else. Some people like dark matter in disk. I didn't say that. Okay, and so like Gus is right here, and Sarah Jefferson, who I think is here. There she is. She's right. Ramesh's head is right in the way. Sorry, Sarah. It's hard with masks. You can only see a little bit of somebody's face. So anyway, so many people here, but in particular Gus and Sarah, are working on their own synthetic Milky Ways, and maybe there are features that look vaguely wave-like, and we'll see. We have some students, Alan too, and Ralph Konitska, who's visiting from Germany. Ralph, where you can wait, there's Ralph. Alan's not here. He's an undergraduate. He's off in Germany, I think. Anyway, they're working on various ways to estimate the motion of the wave. I didn't say anything about it oscillating. I only said it existed, right? We don't know if it's oscillating. We don't know if it's migrating in and out. We don't know anything. Okay. Radcliffe is sponsoring a meeting that Joao and Catherine are organizing called the Radcliffe Wave at Radcliffe, which was supposed to take place in 2020, but will take place in 2022. And people like Andy Burkert and many other theorists will come join us here for that. If anybody's very interested, let me know. It's a small meeting, but if you want to help, please come. Okay. And so then, like, are there other waves like this? So one thing I didn't mention about Nessie is that it's toward the inner galaxy in the closest arm to us with the most perpendicular view. So that's the thing you're going to find first, right? And the Radcliffe Wave is toward the outer galaxy in the closest feature to us with the most perpendicular view. So we're going to find it first. So it's actually harder to find other things oscillating. And so it's possible to look at other galaxies. And so Eric Koch, who's maybe also here. There he is. He's right next to Sarah. See, I can't see with the glasses and the mask. Sorry. Okay. So Eric has an ALMA proposal he's working on to extend the extragalactic things that I'll show you in a moment. And then we have the same simulations I mentioned before. And then the question is, what do these waves mean for evolution and star formation history of galaxies? I have no idea. Maybe we should actually make this work in simulations first. But anyway, I don't know. And I just threw this movie in because it just came out the other day and I thought it was great. So this is just showing you a summary of different kinds of streams and globular clusters and small galaxies falling in to the Milky Way, with apologies to Rohan and Charlie and other people here who work on this stuff. We just found this movie from a different group, sorry. But we actually do know, okay, that a lot of stuff hits the Milky Way. And of course, the outer galaxy has much more surface area than the inner galaxy. All right, so cat lovers in the audience are like, why is there a picture of a cat on the handout? So I'm gonna have to tell you, but I can't move on to what the cat is standing on, which is this paper by Shmuel Bialy et al. About the Perseus-Taurus superbubble, until I tell you a little bit more about the improvements in 3D dust mapping. So here's the Radcliffe Wave. As Catherine would say if she were here, it's so 2020. Okay. So what's in 2021 and 2022? Okay, the answer is that some friends in Germany here, this group of like Ensslin and other people, tried this technique called Gaussian processes to improve the resolution of the 3D maps, 3D dust maps, and it worked pretty well. And so then what we did was first to come along and look for individual clouds and try to make what Tom wanted, which is 3D maps of individual molecular clouds. Because if you go from this kind of resolution to this kind of resolution, which is like a parsec scale for pixels in all dimensions, okay, you can actually, that happens to be Perseus, see molecular clouds individual. This is like, I never ever in my lifetime thought I was going to see this. So I thank everyone who was involved in this. And so here's a rogues gallery from Catherine's 2021 paper showing all kinds of famous, very nearby, I should add, molecular clouds in 3D. All those colored spines and stuff have to do with analyzing the density profiles of the clouds, something I'm not going to talk about today, but please ask me if you're interested. What's important here is that that technique where you get the super high resolution only works within like half a kiloparsec of the sun with the Gaia EDR3 kind of data that we have now, and that will get better later. But for the moment, let's look at Perseus and Taurus. Okay? And so on the sky, Perseus is there. The background image is dust, extended long wavelength dust emission, and Taurus is there. And so there's been a long-standing discussion. They have kind of similar velocities. This is where you get to position, position velocity space. So we're getting to four dimensions, right? Okay. They're kind of similar velocities, but not that similar. Like, do they really touch in 3D? You know, probably not, but they kind of look like they do. So this has been confusing. Well, when you actually put them in real 3D space, it turns out, no, they don't touch. And it gets even more interesting than that because they're actually on opposite sides of a roughly spherical cavity. And if you add in the low density gas, you can see that really quite easily. So Shmuel Bialy was probably watching. Thank you, Shmuel. He led this work, and there's all kinds of interesting stuff in the paper about, you know, how many supernovae you need to cause that bubble, et cetera. And it was reduced to this movie, again, for a press release. And so this is supposed to represent some turbulent gas and a big explosion. And this is kind of a data-driven cartoon where you can see Perseus and Taurus. And there's actually sort of a fun ring on one side of the bubble too that I'll show you later. It turns out to be the intersection with the local bubble. But anyway, so that's Perseus and Taurus are on opposite sides of the bubble. These other ones are interesting too, but for the moment, let's just talk about the cat. Okay, so why was the cat sitting on this paper? Because I was trying to make these videos. Okay, and what are these videos? These videos show you that just for fun, when we published this paper in the half-day letters, we thought it would be fun to publish an augmented reality view of this bubble. And so this is actually a rotating, plot that you can interact with the way that I showed you the Radcliffe Wave one. Again, output from glue to Plotly. But here what we did was we made it so that you can use your phone, and Mike Foley and I both have these that we can show you afterwards. So on the left-hand side, you can just make the data float above any flat surface and walk around it and look at it. And then on the right-hand side, you can use the thing I have in my hand, which is called the target cube. And you can actually move the 3D data around, and you just have to look at the cube with your phone. And so this is all free software. And I think if you're going to try to understand projections and overlaps and 3D structures, I personally like that very much. And actually it passed, I know Charlie's listening, it's passed the Charlie Ladder test, which is Charlie is not Mr. Pro Technology. And the first time we showed that to Charlie, he asked where he could get one. They're $15 on Amazon. Okay. So we collaborated with a commercial company called Delightex that makes some software called CoSpaces, which is free to you, that you can use to see that. And like I said, you can ask for a demo, and we can also show you the 2D data that show you the hot gas filling the shell and all the other interesting phenomena. But here I'm trying to just concentrate on 3D structure. Okay, so finally, how about position, 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 velocity, 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 6D data, right? So there's the cat, but I'm going to try to show you something that's even better than a cat. And in particular, I'm going to show you, this is an interactive figure, which I would click on, but I think I'm going to suspend that for a moment and give you a little bit more information first. So what I'm going to do is I'm going to confess, okay? So a few years ago, I ran a conference at Radcliffe called The Undiscovered. And the whole point of it was how many discoveries, especially the really fun ones and the really great ones in science, were not quite accidents, but you were sort of looking for one thing and you found something else. The acceleration of the universe would be the best example, right? So this was, yes, this result was in the Times a few weeks ago. That was very exciting, but no, that's nonsense, okay? What were we really doing, okay? What we were really doing was Joelle and I said, okay, we're like the old people in this collaboration, and now we know where all these clouds are in 3D, and we know all this stuff. We should be nice, and we should write some article about the structure of the local Milky Way for like Scientific American or Wired or something like that. And so we better start by putting everything where it goes in 3D, because we just had this kind of gallery, right? We didn't actually look to see where all these clouds were. And so I kind of told you the story out of order because the Perseus Taurus thing sort of happened at the same time as this one. You'll see why. All right, so this is a little video that they made us dig up from the press conference of a year ago when we were again using glue over Zoom and just kind of putting data together. And so this is the first view that we had of these yellow things are the dense clouds. The light blue thing is a model for a cavity, the local bubble, using these lichen Ensslin 3D dust maps. It was actually made by other people, not by us. Okay, so just to make it clear, our contribution to this story is that the star point regions are on the surface, not the map of the Dennis hopefully got wrong in the online version of the article, but he corrected it. Thank you, Dennis. So anyway, right, so this was kind of surprising, right? We were just trying to say, where are these things? And then it turns out that like every single nearby star forming region is on the surface of the local bubble. So that's kind of crazy. And so we had some fun with this. And so here are the slides that Catherine showed at the recent AAS meeting that was only the press conferences. So this is again a data-driven cartoon where you can see the famous star forming regions lying on the surface of the local bubble. And just, you know, for those of you who don't work on this kind of stuff, what we're talking about here is like if you see a beautiful image of, say, the star formation region in Ophiuchus, that's sort of like a 10 times zoom in from what you're looking at here. And, you know, if you're talking about like disks in Taurus and Alma, you know, it's like a 10,000 times zoom from what we're talking about in this little dots in the cartoon. So, right, so what this means is that we know, not only do we know about the geometry of the local bubble, but this time I'm going to use the velocity. So I'm going to show you what we know from looking at the star clusters expanding. And I'll show you the interactive figure live in a minute, but let me just show you kind of what we think happened. So 14 million years ago, right, you have some cluster, which we think we know which one, has a bunch of massive stars in it that go supernova and they start creating a local bubble. And then what you'll see when I show you the interactive figure is that the other clusters that are associated with the regions forming young stars now actually form and move in exactly the right way if those clouds form on the surface of this bubble as it expanded. So that was expected by people like Chris McKee and Jerry Osterreicher, and I'll show you that in a minute, but not really expected that we would be able to observe it so cleanly. Okay, so now I'll just show you the cartoon next to the real data. That's a movie of the interactive figure. Let me show you what the interactive figure actually does. Click on this. I'll try the interactive figure. So this is another one of these things made by Catherine from Glue to Plotly. So here's, you can see that fine, right? Okay, so there's the bubble. I think it's clear the blue is the bubble. Okay, these are sort of landmarks in the history, but I'm just going to do it this way. Okay, so if I slide this back to 17 million years, you can see the first cluster. So these are the first two clusters here, these two dots, okay? And those are the ones where we think the supernova originated, right? And then the bubble starts forming. And then what's hard to see in 2D, unless I rotate this around, is that these things are actually on the surface. So the little dots that you see are like the current position of a formed cluster. And then the trail behind them is where they came from. And you'll notice also, I'm about to show that to you in the kind of cartoons too, but you see the sun is this yellow thing that's coming toward the bubble and moving into the bubble about 5 million years ago. And then if I turn off all the extra dust, you can see that these little dots are kind of exactly on the surface of that bubble itself. So the dots, just to reiterate, are measured from stars, okay, from Gaia 3D measurements with radial velocities included. And so we actually, that's the 3 dimensions, okay? We know 3 dimensions of velocity. We also know the velocity of the gas, which is what Ralph is working on in the Radcliffe Wave, but we'll talk about that later. So if you looked at if you could zoom outside the galaxy, which would be so convenient, and you looked at the clouds, those are the green dots, and the local bubble, they would look like that. And then of course, if you looked at it from inside the galaxy, it's just everywhere. Okay, so you certainly can't discover this phenomenon by looking at the sky because the local bubble or inside the local bubble, it's kind of a problem. It's not in some direction on the sky. All right, so the thing about the sun that I told you is kind of interesting. So the sun is in the middle, very close to exactly in the middle of the local bubble right now. Right, about 5 million years ago in this model is when it would have crossed into that region. And, you know, at first you say that's kind of bad, right? Because you never want to be, the sun and the earth should not be special in any story, right? I just got that one right. And so anyway, the way to fix that is to just say that there are bubbles everywhere. Okay? And we already know, I'll show you in a second in another interactive figure, that the per tau bubble is touching this bubble. Some bubbles in Orion that Mike is working on that I heard talk about this morning. I didn't even know you could do that. Thank you. are also touching this bubble. And so this is just shown as an isolated bubble in these cartoons, but it is not. And just for fun, I'll mention that there's a whole group who works on radioactivity in the Earth's crust and the timeline of the enhancement of radioactive elements that would be caused by the Earth traveling into this bubble lines up with the timeline in this story. So, okay, great. I think this is fun. And it means that, like I said, all the young stars within half a kiloparsec of the sun are forming on the surface of the local bubble. We think we know how this happened. And it says here evidence for a 50-year-old theory. I'll remind you what that is. On the one hand, with the work of Jerry Oestreicher and Chris McKee over here, and on the other hand, with the work of Eve Oestreicher, which is much more recent. So those of you who have taken any interstellar medium class have seen this picture, okay, of the phases of the interstellar medium. And the idea is that there's these huge supernova-driven bubbles and then cold clouds roughly at their surface. And then this is much less roughly. Here's a simulation where you're looking at these things forming from the top down. And these little dots are actually stars of different ages. And so one can start looking at whether or not these details are consistent with what's now been observed. But just for fun, here's an edge-on view, and you can see the bubble almost kind of blowing out of the galaxy, and that's just the slice through the Milky Way. So theorists would have known this for a long time, but I'm sorry, it took us a really long time to get me the data. Okay, so now let me show you something that isn't published because my collaborators probably correctly said, do not put this in the paper, it's too insane. So I will show you what is insane. We have very few measurements of the motion, the transverse motion of the Radcliffe wave and of this thing, which is, remember I said there was some other dense gas when I showed you the Radcliffe wave? That's called the split. It was found by Lallemont et al. It's another long straight feature. So if I turn this around, let me just turn off some stuff. Turn off the bubble. If I play with this a little bit, you'll see there's these two kind of long features. The purple thing, I'm sorry that it's purple, it should be green, but the per tau bubble we know is green. But let me just show you for a moment because I promised, but you see how the per tau bubble also makes a dent in the local bubble? And you even, when Shmuel Bialy was looking at the velocities of Taurus, which is here, and Perseus, which is here, he didn't understand in the gas why they weren't going like this. They were kind of going like this. And the answer is because the local bubble is pushing harder than the per tau bubble. So that's kind of cool. But that's not what's crazy, okay? What's crazy is that the very few measurements of transverse velocity that are down here in Orion and up here in the split suggest that if you go backwards in time, sorry, let's get rid of this. So apparently there's a lot of crap on. Okay, anyway, if we go back in time, okay, the Radcliffe wave and the split would actually intersect, okay? And if there were these local long features that crossed through each other in the plane of the Milky Way, that would cause some huge enhancement of dense gas, which would then cause that cluster, which starts at that green position is where they cross, to form. And then you'll notice that the surface of the bubble and the clouds stay kind of right aligned. Oh, I turned off the gas, sorry about that. Well, anyway, we're running out of time, so never mind. But there's this crazy theory, okay, idea, to call it a theory is too generous, okay, that it could be that we even know what caused the original bout of star formation that caused the local bubble. That would be the intersection of these filaments. And Gus has made the point that there are very few, if any, models of a galaxy that would have things moving radially that much. And so this may be a huge problem, but if it turns out to be true, that'll be really fun. Okay, so we gotta find some other bubbles. We gotta look for interactions. We have no idea what this has to do with spiral structure or galaxy evolution. And then last but not least, again, I heard that Mike told you about this morning, but it turns out if you pick apart the nearest massive star forming region, Orion, in huge detail, looking at 3D dust and 2D images of all different wavelengths, you can actually put together quite a picture of what happened and where the X-ray emission comes from and where the H-alpha emission comes from. And that's what Mike is working on to rethink Barnard's loop. Okay, so last but not least, how about other galaxies? Wouldn't it be much easier to look at this from outside of a galaxy? Well, yeah, it would. But the problem is that as gorgeous as all of this imagery is, it has 100 parsec resolution. Okay, so 1 arc second. Yes, I am complaining about 1 arc second resolution. Okay, so 1 arc second resolution that you can get with surveys like FANGS or the ALMA data that you see here is not quite good enough, right? So the resolution I just showed you of individual clouds is 1 parsec, right? That's 100 parsecs for nearby galaxies. If we get to 10 parsecs, starts to be really interesting, which is why people should select Eric's proposal. Okay, but you know, it may be possible. And just for fun, JWST apparently is also interested in this, and I'd like to report that the follow-up to the FANG survey, apparently the data from JWST that will zoom in the regions that HST can't see will be public essentially immediately. So I haven't mentioned the logos at the bottom of the slide as I've been going along, but a lot of them said Dataverse. So that's a Harvard-centered data sharing enterprise that some people here use. And all of the data and all of the glue files, the macros that let you do what we did here are all shared and registered with the papers in the Dataverse. And so I'm a big fan of JWST giving away all the data for that follower survey. So here's just everything I didn't have time to tell you that's going on as follow-up now to all of these things. Okay, and so I've introduced a bunch of these people who are here. So Gus Bean and Mike Foley are both working on simulations, and Mike also on data. Ralph, as I mentioned, is trying to fit models of the motion in the plane of the Radcliffe Wave and also out of the plane. We have an RAU student who's going to come work with Jesse Hahn about the magnetic field on the surface of the local bubble, which is really cool. Ask me about that. Another student did his senior thesis looking at mass size relations when you look at clouds in 3D instead of 2D. And yes, they're very different. I mentioned Eric's interest in a 10 parsec resolution ALMA survey. Alan is the student who's working on the oscillating Radcliffe Wave. And then Sarah here and Maya Skarbinski is another undergraduate, are working on cloud mergers, and that paper's almost done. And then last but not least, Pat Udonverser runs the Worldwide Telescope Ambassadors Program, some of you may know about here. And we have a big grant from NASA to do this thing called Cosmic Data Stories, where we try to make data science interesting by using real astronomy data. And so the Radcliffe Wave will actually become one of these data stories that high school and college students will use soon. So that's what I wanted to tell you. And I actually have glue running here in the background just to show you that this is real. So just for fun, I have the per tau session open. And yes, Peter, I thought I'd show the Worldwide Telescope plugin inside of glue. And isn't it annoying how Zoom always puts the controls over the controls? Okay. So, here are the figures that were output to augmented reality. This is how easy it is to, bring in additional data. These are actually 3D plots where you can move stuff back and forward. And I didn't really emphasize, and this is showing you the data sets all glued together. So there's not some master file that's doing this. All of the data sets are talking to each other. And so just to tell you, glue in like 2 sentences, the meaning of glue, it's not an acronym, has 3 meanings, is to join together a whole bunch of data sets of the kinds you just saw, okay? To join together plots, so you can make live selections in one plot, and then to join together software tools. And so you just saw me very quickly show you Worldwide Telescope embedded inside of glue. And so you can embed whatever, web-based or other software you want. I'm going to stop talking now because that was exactly 55. Thank you.
Okay. So we must have some questions first from the audience. Yeah.
Great talk, Alyssa, although knowing that it's your talk, I'm not that surprised. But the question I have been thinking about while you've been talking is, if you had several supernovae go off, close together in time and space, they probably were resident in a giant molecular cloud with a huge amount of mass. So I guess my question would be, is what's the relation between the mass that we see on the bubble of all the star forming regions that we all know and love, and the original mass in the cloud that hosted those
Yeah.
supernovas?
Well, as Phil complimented me, I will compliment him back. Whenever Phil asks a question, you know it's going to be a good question like that. Okay, so that's a good question.
Could
in
you
that-
repeat the question just in
Oh,
case?
sorry. The question was essentially, how does the gas get rearranged? So in other words, if there was a giant molecular cloud that led to the formation of the stars that led to the formation of the bubble, what happened is that molecular cloud gets spread all over and become the next generation of molecular clouds. So the question really, I think, is like, what's the ratio of stuff that was moved there from an original dense blob to stuff that was low density that just kind of got swept up? And so for the per tau shell, we actually made a quick calculation of if you had like very low density stuff and then you just swept it up into Perseus and Taurus, would you have enough stuff? And the answer is yes, actually. So you don't need but we didn't do that, at least that I know. Maybe Catherine or Joao was listening and they can answer. I don't remember doing exactly the same thing for the local bubble, partially because the top and the bottom are missing. But it'll be really interesting to do that in the simulations. And I don't know, do you guys have?
Yeah, we're seeing that. Yeah, that's exactly what you see. It's basically, especially like in my simulations, similar to this. Sorry,
Mike Green's right.
Yeah, basically feedback from radiation and winds is what really slows down. Star formation ejects a lot of the gas, and the supernova kind of finishes it off. So basically, you find that the wind feedback and radiation feedback in the massive stars is what really punches star formation, and supernovae arrive too late. So, but yeah, with the simulation, we have.
So do you think that some of the cloud would have been already dispersed?
It depends where, yeah, I mean, it depends on where the
I mean, in
formation is
Eve's
happening.
simulations also,
Yeah.
the ones I showed very briefly, you do see something like that. And Mike has this gorgeous movie, Mike Green jokes on your slides.
Yeah, and I'm
Yeah.
finding too in like, so they've done like Milky Way clouds, whereas I'm doing denser clouds, and we're finding that when you form one of these very massive stars, you actually can't eject the gas a lot faster. So I'm finding that the cloud is destroyed within a maybe.
So I guess for the people on Zoom who can't hear, what Anna Rosen is saying is that the clouds are destroyed a lot by
Yeah.
just the massive stars being in them before they go supernova. right?
Yeah, so I think in my simulation, about 20 to 50% of the mass is at the end of the simulation is ionized mass.
Yeah, the other thing I find really surprising about the simulation, which we talk about another time, is that the bipolar outflows from the low mass stars do a lot. That's, I've
I
always
think the
wanted
ones
that to
you-
be true, but
You do
Doesn't-
see that, it's mostly the massive stars, so like
With
where
bipolar
where we
outflows.
see the sites of mass star formation, those are the ones that are really pushing material out of the cloud.
God.
Yeah,
Well, so, but anyway, just thank you, Ann. To follow up, Phil, right, if the crazy thing is right, then also you don't necessarily have kind of a boring, sorry, but quiescent, GMC sitting there. You have some colliding stream like our dearest friends wanted all this time. By the way, which is what you also have at the surface of the shell that's giving you all this additional star formation. So, what's the chicken and what's the egg? I don't really know. It's a good question.
This is just a kind of follow-up to that. Does this end up predicting that there's a 18, 20 million year old association sitting there somewhere that we should still be somewhat coherent?
Well, there sort of is. That's what this UCL, CC, I never remember the names of them. Wow, help me, where are you? That's what they sort of are. But then there would be additional associations, and then Mike, I remember, but Cameron Sweden, who's working with Joao and other people working with Joao, like Stefan, my guess, they're really looking now to put these kind of clusters back together, and they're really looking forward to the ER3 from Gaia to have even better data with more radio velocity. So those are exactly the kind of questions that I'm going. Other than, yeah, there sort of is, I can't say.
Okay, let's give the Zoomers the chance.
Oh, yeah.
Yeah, so Jonathan Slavan on Zoom asks, is the local bubble, as you show, consistent with what is seen in CA2 and NA1 absorption?
Yes.
He notes that it appears larger. And have you considered the role of the loop one bubble?
Well, yes, and yes. So, yes, in the paper that presents that 3D dust-driven model of the local bubble, which again is not ours, there's comparisons there, and also in the extremely extensive response to the referee that Catherine published in Nature. Because one of the referees loved our paper, and the other referee was a local bubble expert. We know who it was, but I won't say the name, who hated our paper. And so Catherine had to go into every bit of detail about the prior knowledge of the local bubble. And so, yes, is the answer. It's consistent with all of that. And then loop one, we think, Mike, do you remember exactly what the geometric association is? Loop one in the local bubble. I know we discussed this. I don't remember. No, it's nearby. Whether or not it's interacting or touching, I don't know. This again, my memory is not good enough, but we looked at it, and yes, it's kind of in the field of view.
Another question from Zoom from Tony Stark. So he notes that there are these low density regions and high density regions, and they're threaded by molecular clouds. Such a thing is going to have the Parker instability, which will have a characteristic size around 1 kiloparsec.
Yes.
If you're looking at a small piece of it, it'll look locally periodic. So basically, what about the magnetic field?
Yes, and so we were talking about this at Charlie's birthday meeting in the fall of 2019, just before the pandemic, and Telemachus Mischievous was there. And so there was a lot of what about the magnetic field? And so we looked into Parker instabilities, Rayleigh-Taylor instability, et cetera, and the geometry wasn't quite right for any of those. But on the other hand, I will say that what I'm really looking forward to in not only this youth project, but there's a big collaboration that involves Cal Caselli and Andy Burkhardt and Joao and people in Europe who are interested in mapping out the 3D magnetic field of the surface of the local bubble, because you realize there's a very easy way to do this, which is you say you know exactly where the surface is. Then you have all these measures of the plane of the sky magnetic field, right? But then you say, well, I actually know the inclination of the field if you assume it's in the surface of the bubble, right? And then you could actually like measure the divergence of the field and stuff on the surface of the bubble. So this is another one of these things like 3D dust mapping where it's easy to say, but maybe a little hard to do. But anyway, we're going to try that this summer. So where's Jetson?
Since the distances from can you speak just a little bit about, since the major parallax distances on the 3D dust mapping distances are so close, what does that tell us about the dust properties? Like, do we know them really well, or how well did they distribute from the 3D dust?
Well, very well. And I'm going to let Doug answer that question.
Could you repeat the question?
Doug can't just sit there silently. You can repeat the question too. Because Doug's done a lot.
Well, you got the microphone.
Okay, I'll come close to I know what he might say, but why don't we let him say?
So the question was, can we learn things about the properties of the dust itself from the fact that the Maser distances and the 3D dust distances do so well? But the 3D dust distances are, tied to understanding the stellar models and how they get written by the dust and so on. But then those stellar positions are tied to Gaia parallaxes. At least we did all this before Gaia. Actually, don't have to use Gaia, but if you include Gaia parallaxes, it's much tighter constraint. So I think the answer is kind of, you don't have to actually know much about the dust properties. You kind of get a pretty good answer, but you can turn this around and say, now I want to measure the Redning law parameter RD as a function of distance and position, 3D. And so we've done things like that too.
There's a whole bunch of other papers using the 3D dust data about dust properties. So I agree with Doug. The Maser coincidence that coincides, doesn't matter very much. But the question is still interesting because we learn a lot about the 3D distribution of dust properties. Other like that, which of course the insurance cost. And the friends, by the way, are great, green and egg schlock.
Did you have a question, Ramesh?
Yeah. Great stuff, Alyssa. But it's also clear that you didn't say it all. There were things that you kind of put away. And there was one thing from your abstract I was waiting to hear.
Okay, what does it say?
Because among other things, it says interactions of massive extragalactic objects with the Milky Way.
Yes.
So are any of your features actually caused by something else bashing the?
Well, Gus.
Yeah.
So Gus has a paper that I learned about during his first week in graduate school, before we published the Radcliffe Wave. It says that you can't get these things from, say, Sagittarius or crashing in the Milky Way. But the issue, my issue is that the wavelength looks really long, but Gus points out that, well, maybe you can have like harmonics and extra modes on this otherwise long. But Gus, you want to give it, I'll come next to you. You wanna give it-
Go for it.
Well, so, yeah, I mean, there's a long history of people looking at how this responds to the satellites coming in. The thing with this is, it's a gas-based feature, and so you would need a simulation with gas, which I don't think anyone has looked at it in enough resolution to say anything about the Radcliffe Wave. The other thing is that if it's something like Sagittarius, its last Paris-Center passage was quite a long time ago, like a year ago. And so it's not just, you can't just look at, say, how the disk responds to the initial phase. You also have to look at the evolution of the disk, the evolution of the gas. So the answer is it could happen, but no one has shown it explicitly.
And you
But
also.
the idea is you take the gas disk of the galaxy and you just send a satellite through and it leaves behind a wake or a wave or something.
Yeah, so initially, when the satellite comes in, it does exactly that. And then what happens is you get these large scale sort of undulations throughout the disk. And then the way that the disk responds to that is those large scale undulations become smaller scale undulations. And that's how like this sort of like vertical energy is anticipated throughout the galaxy. On a long enough time scale, the galaxy just becomes a little bit puffed up. Introducing vertical energy.
Great.
Yeah, I think I was talking too fast, that's why I showed
That's
this.
it. Yeah, nice.
Right. But I didn't say
the
much, and
connection.
I also forgot to say something really important, which is the reason I called it the new Milky Way, isn't that we're so proud of ourselves, but that most of the structure, all of them, are very recent. Okay, these are tens of millions of years, not tens of billions of years. These are like, instantaneous things that happen. And so a lot of simulations, like Gus is suggesting, need very detailed physics to see that kind of short time scale.
Okay, we should cut off at 5:15, which is now, unless there's another really pressing question from anyone, a short, important question, we can,
I also have to thank my mother for asking me to put Milky Way bars on that. Remember, and also, I have lots of glue swag. If anybody wants to remember to ask us more about the software, so come and ask us if it's ready to come in reality.
okay, thank you again.
You want to see what a birch cube looks like?
Oh, Doug Rogers too.
So now you have a new name.
Yeah, yeah.
You want us to-